Hello and welcome back to my channel, ELECTRO-MASTER. As promised in the previous video, where we discussed how a contactor works, today we continue with an exciting new episode. We'll explore how an inductive sensor works and how to achieve control via radio waves using a remote control and receiver. Stay tuned to discover all the details and practical applications of these components. This is a PNP-type inductive sensor, a widely used device in industrial automation for detecting metal objects without physical contact. But how does it actually work? The inductive sensor emits an electromagnetic field in its detection zone. When a metal object enters this field, the sensor detects the change and sends an electrical signal. In the case of a PNP sensor, this signal is positive, meaning it supplies voltage to the controlled circuit. Inductive sensors are available in two main types: PNP, which sends a positive signal, NPN, which sends a negative signal when it detects an object. These sensors typically operate at voltages of 12-24 VDC, but there are also variants designed for other voltage ranges depending on the application. They are extremely durable and reliable, making them ideal for harsh industrial environments, as they have no moving parts and do not require physical contact with the detected objects. Next, I will show you how to connect and use this sensor in practical applications to better understand its usefulness in the world of automation. An intermediate relay is an electromagnetic device used to control more complex circuits. Essentially, it acts as a bridge between two circuits, allowing the control of a higher power or isolated circuit using a low-power control signal. How does it work? An intermediate relay consists of an electromagnetic coil and a set of contacts, usually NO, normally open, and NC, normally closed. When the coil is energized, it creates a magnetic field that attracts a movable core, changing the state of the contacts. For example, normally open contacts will close, and normally closed contacts will open. Types of intermediate relays: electromagnetic, the most common, with mechanical actuation. Solid state, SSR, without moving parts, operating electronically, being faster and more resistant to wear. Operating voltages, intermediate relays can operate at different voltages, the most common being 12V, 24V DC for low voltage applications. 110V, 230V AC for industrial or household applications. This relay is crucial in this circuit because it isolates the inductive sensor from the contactor, protecting the components and ensuring reliable operation. This is a contactor, but we already discussed it in the previous video, so let's move on. We already discussed the timer relay in the previous video. Let's move on. To power the PNP sensor, I will use a 24V DC supply. A 24V DC power supply is commonly used in industrial and automation applications because it's safe, efficient, and widely available. This voltage is ideal for sensors like the PNP inductive sensor, which operates at low power but requires a stable DC source to function correctly. By using 24V DC, we ensure the sensor has the necessary power to detect objects and send signals to the relay or other connected devices. In this case, the PNP sensor uses three conductors: brown, positive, blue, a negative, and black, output positive. Brown, positive. This conductor is connected to the positive terminal of the 24V DC power supply, providing the necessary voltage for the sensor to operate. Blue, negative. The blue wire is connected to negative terminal of the 24V DC power supply, completing the electrical circuit. Black, output positive. The black wire is the output of the sensor. It sends a positive signal, when the sensor is activated, to the connected control system or relay, indicating detection of an object or event. This wiring configuration allows the PNP sensor to function correctly by providing both the power input and the output signal in a safe, reliable manner. I will supply the contactor coil with 230V AC, and the circuit will be connected through the normally open NO contact of the intermediate relay. This means that when the intermediate relay is activated, the normally open NO contact will close, allowing current to reach the contactor coil and power it. This will activate the contactor, enabling it to switch the connected power circuits, such as motors or industrial equipment. On the other hand, if the intermediate relay is not activated, the normally open contact remains open and the contactor coil will not be powered, so the contactor will not operate. This connection ensures control of the contactor activation through the intermediate relay, based on the signal received from the PNP sensor or other components of the system. In this case, we will connect an incandescent bulb to the contactor's power contacts, powered by a 230V voltage. The power contacts are responsible for controlling the main power circuit of the contactor and allow current to flow to the connected load, in this case, the incandescent bulb. How it works: when the contactor's coil is powered with 230V AC through the intermediate relay, the power contacts will close and allow the current to pass through to the incandescent bulb. The bulb will begin to light up as the electric current flows through its filament, generating heat and light. If the power to the contactor's coil is interrupted, for example, when the intermediate relay deactivates, the contactor's power contacts will open, cutting off the bulb's power supply. As a result, the bulb will stop lighting. To make this setup more interesting, I will add a time relay, which, depending on its settings, will keep the contactor activated for a specific period of time. Here's how it works. Initial activation. When the system is powered on, the time relay starts its timing cycle. This relay is connected in such a way that it controls the contactor's activation. Time-delayed activation. Once activated, the time relay will keep the contactor energized for the duration set on the relay. For example, if the time is set to 5 minutes, the contactor will stay activated for 5 minutes after it receives the initial start signal. Contactor holding function. The time relay essentially holds the contactor in the on state during the set time, even if the initial activation signal, such as a start button, is no longer present. This ensures that the circuit stays closed and the load, such as a motor or light, remains powered for the desired time. Automatic deactivation. After the preset time has elapsed, the time relay will open its contacts, cutting power to the contactor's coil and causing the contactor to release, turning off the load. Adjustable time control. Depending on the settings of the time relay, the duration the contactor stays activated can be adjusted. This gives you the flexibility to control how long certain equipment or processes will run after the initial start signal. This time delay feature adds another layer of control to the circuit, allowing for automated operation that can be crucial in industrial applications where precise timing is needed. As you can see, I have connected the normally open, NO, contact of the intermediate relay to the auxiliary contact of the contactor. This arrangement ensures the start function of the circuit. The time relay will cut off the holding circuit after a preset time. This means that after the set time has elapsed, the relay will open its contacts, interrupting the current to the auxiliary contact of the contactor. As a result, the contactor will be deactivated, and the circuit will stop, ensuring a time-controlled operation. Next, I will replace the inductive sensor with a remote control activation kit using radio frequency. This kit consists of two main components, the remote control, as the transmitter, and the receiver module. The remote control will be used to send a radio signal to the receiver module, which will receive the signal and command the circuit activation. The receiver module will be connected to the auxiliary contact of the contactor, and when the signal is received, it will activate the contactor. This type of radio frequency control allows remote control of the circuit without physical contact with the electrical components. This control method is very useful in applications where quick and safe operation is required, without direct intervention in the installation. Just like with the inductive sensor, the normally open, NO, contact of the intermediate relay will be connected to the auxiliary contact of the contactor. This connection will allow the contactor to be activated when the signal from the radio frequency receiver is received. Specifically, when the remote control sends the signal, the receiver activates the intermediate relay, and its NO contact will close the circuit, turning on the contactor. Thus, the circuit will be activated via the radio signal, and the operation will be similar to that of the inductive sensor, but with the advantage of no physical connection being required for control. This solution offers more flexibility and convenience, allowing remote control of the circuit. That's all for this video. I hope you enjoyed it and learned something new about our circuit with the contactor, intermediate relay, and radio frequency control. If you liked this tutorial, don't forget to give it a like and leave a comment below with your thoughts or any questions about the topic discussed. If you want to stay updated with future tutorials, make sure to subscribe to the ELECTRO-MASTER channel and turn on notifications. In the next video, we will talk about the photoelectric sensor, image receiver type, and how we can integrate it into our circuits. Thank you for watching, and I look forward to seeing you in the next video.